In our next section, we're going to talk about three different features in Layer 2 security on the Catalyst switches that go hand in hand, which are specifically the dhcp snooping, the dynamic ARP inspection, and the IP source guard features. Now, before we get into the details of specifically what are the features and how do we configure them, I want to spend a minute talking about what is the problem that we are trying to prevent to begin with that has to do with Layer 2 and Layer 3 spoofing attacks that can happen on the LAN segment in order to implement what we call a man-in-the-middle attack. Now, if we were to look at the LAN segment from a high-level functional overview where we have the default gateway that we're trying to route our traffic out of in order to get to the rest of the network, and then we have a victim and we have an attacker that is locally located on the LAN segment. Now, one of the things that's important to understand about this attack is that the attacker needs physical access to the LAN segment in order to implement it. So it's not something that would normally happen like in data center type environments or based on certain physical security situations. You may be able to inherently prevent this. But for any type of normal enterprise environment where maybe you have like a shared meeting room or any case where devices are on the physical shared LAN together, wired onto the LAN, then they're able to potentially implement this attack unless we use the features to prevent it. Now, we're assuming here when we're routing IPv4, and we'll talk about this later in the case of IPv6, it's a very similar type of attack that we're trying to prevent, that the victim comes onto the network, and the first thing that it tries to do is to get a DHCP address. So the victim sends out what we call the DHCP discover message. Now, let's assume that in this design, we have the Layer 3 gateway on the LAN, and then behind the LAN, we have the DHCP server somewhere centrally located in the network, where the router here is going to be using the IP helper address. It's receiving the DHCP discover and then forwarding it on to some remote segment where the centralized DHCP server is located. Now, under normal operations, when we have the regular DHCP that is functioning properly, what we should see is that the DHCP discover gets broadcasted from the victim out onto the LAN segment or the end host onto the LAN. Then the Layer 2 LAN switch is going to send this everywhere because it's a broadcast. The default gateway is going to pick this up. It's going to say the destination is all broadcast, but it is the DHCP discover. So I'm going to convert this from a broadcast to a unicast. And with the IP helper address, I'm going to forward it towards the DHCP server. Now, the DHCP server is going to get the request, and it says, okay, I'm going to service that pool, so I'm going to reply back with a DHCP offer. The original source that sent the discover is then going to reply with a DHCP request to say to the server, yes, I actually want that address. Then the server is going to reply back with the acknowledgement, which is the actual assignment. So it's a four-step process: the discover, the offer, the request, and the acknowledgement. Now, the potential issue that we run into is that when the discover is sent, since it is a broadcast, the Layer 2 switch is going to send it everywhere. Now, we have this other device on the LAN segment on the right. We have the attacker that when the LAN switch is sending those messages out, they're going in both directions. They're going up towards the default gateway, and they're going across the LAN to the attacker. Now, when we look at this from a response time point of view, normally the attacker is going to receive the frame before the DHCP server does, simply based on the processing delay of the packet. Because the router is going to have to receive the broadcast in, it's going to have to do a conversion from a broadcast to a unicast, forward it to the server needs to process it, and then send it back. Now, when you look at the order of operations of DHCP, it is valid for the end host to send out a discover and then get multiple offers back in. And normally the way the end application works, like Windows, for example, is going to choose the offer that came in first based on the delay or the order of the packets. So what this means is that if the attacker is running a DHCP server itself and it replies back to the victim with an offer, the victim is then going to reply with a request, and the attacker can send the acknowledgement. Now, if the attacker is the one that's assigning the DHCP address, what does this mean about the potential traffic flow patterns onto the LAN segment? Where normally we would send the traffic from the victim to the router, and the router would forward it on to the rest of the IP network. But if we have someone else that is controlling the DHCP pool, essentially what they're able to do is to say, when I give you the DHCP lease, I'm going to tell you that your IP address is in the correct pool. So let's say, for example, that this network is 192.168.0.0/24. So I'm going to give you a legitimate allocation. Maybe I give you .10 as your IP address, but I'm going to tell you that the default gateway is .2, which is me. The router being .1 on the segment, that's supposed to be the legitimate gateway, but now we're offering them all of the other correct options. We're giving them the correct IP address pool, we're giving them the correct DNS server, or maybe the DNS server is the attacker itself, which means that when we go to resolve a website, we might be able to do a man-in-the-middle attack based on that. Well, let's say we have, whatever, www.yourbank.com, and when we go to do a DNS resolution to this, if the DNS request goes this direction, the attacker can then reply with whatever spoofed server that it wants, and then it redirects the traffic to some alternate destination. Now also, we can force the victim to send the traffic this direction before the attacker rewrites the frame to go to the default gateway, which is essentially a man-in-the-middle attack. So the attacker is then able to sniff all of the traffic. Anything in clear text, like clear text passwords, we would be able to capture those, or we could do the redirection attack based on DNS. Now, you'll see that in certain circumstances, this happens on accident. Like if someone plugs in a SOHO router, like a Linksys access point into the network, and it's running a DHCP pool, it's going to start to give allocations onto clients on the LAN segment that it's not supposed to. So in certain cases, this might be just a misconfiguration. In other cases, it's a malicious attack where someone is trying to redirect the traffic flow from man-in-the-middle, or to redirect the DNS request and response in order to do man-in-the-middle to some spoofed server on the internet. But in either case, the way to prevent this is going to be with the combination of these three features: DHCP snooping, dynamic ARP inspection, and IP source guard. Now, the first of which, DHCP snooping, is going to prevent the spoofing of the DHCP server and prevent against a DHCP exhaustion attack. Now, what an exhaustion attack is when the attacker sends out DHCP requests over and over and over and tries to lease every single address that's in the DHCP pool. Now, once the attacker leases all of the addresses and there's none left, then once it hears additional DHCP discovers, it can respond back from its own pool in order to do the man-in-the-middle attack. So whether it's rewriting just the default gateway or whether it's rewriting the DNS server, either way, the attacker is going to have control over the traffic patterns. Now, specifically, the way that the feature prevents this is to enforce what links a DHCP discover message will be allowed on. So in our particular case, what we would be doing here is to enable DHCP snooping on the switch, and we would say that the link up to the default gateway is a trusted link, and the other ports are untrusted. Now, specifically what this means is that when we're listening for the DHCP traffic, so the discover comes in, and we forward it towards the trusted port, and if we were to forward it in this direction and an offer came back in, we would simply drop that packet. So in other words, the discover is only allowed to go to the legitimate DHCP port, the one that is trusted, and the offers are only allowed to come back in on the trusted ports. So simply based on filtering where the packets are going in the DHCP discover messages, then we're able to prevent the attack. Now, additionally, when the switch receives the offer back inbound, it's going to maintain a mapping table that contains the IP address that was assigned, the MAC address that requested the DHCP lease, and the local port that they're configured on. Now, we'll see specifically why it does this. It's to then enforce later, through dynamic ARP inspection and IP source guard, security in the data plane. So with DHCP snooping, we're only enforcing this in the control plane. We're saying that who is allowed to receive the DHCP discover messages, and then where do we keep the binding table of the mappings between them. So who owns what IP, who owns what MAC address, and what particular port that are they located on. Now, specifically, the way that we configure this is going to be three main commands. We have IP DHCP snooping in global config, IP DHCP snooping for the VLAN, and then IP DHCP snooping trust at the physical port level. Now, in our particular case, what we're going to be doing is configuring DHCP snooping on switch 1. And switch 1 has the physical link that also goes to the rest of the CSRs. So let's say on router 1 that we're going to configure it as a DHCP server. And then we're going to configure switches 2, 3, and 4 as DHCP clients and see what happens when we turn the feature on and how it affects the data plane forwarding between them. So first thing we're going to do is just make sure we have basic layer 2 connectivity between the switches. So on all the switches, I'm going to go to their ports, range, interface range fast Ethernet 19 to 24. Actually, I'm going to say default interface range, those ports. Okay, then on those particular ports, we're going to say that they are switch ports. And the switch port access VLAN, let's say, is 10. Okay, then we're going to create a sub-interface on router 1. Router 1 is going to have interface gig1.10, encapsulation .1q10. IP address is 192.168.10.1. We'll say on switch 1, likewise, we have a VLAN interface, VLAN 10. IP address is 192.168.10. We'll say 11 for switch 1. Actually, 21. And we're going to ping 192.168.10.1, which we can reach. Okay, so we have basic connectivity from switch 1 up to router 1. Router 1 is going to be hosting the DHCP pool, and then the other switches are going to be leasing addresses from it. So next step, we're going to configure the pool on router 1. We'll say we have an IP DHCP pool. We'll say this is VLAN 10. And the IP address, which is the network is 192.168.10.0/24. And the default gateway, okay, default router is going to be router 1, 192.168.10.1. And that's it for now. Okay, the rest of the switches are going to create their VLAN 10 interface and simply say IP address DHCP. Same on switch 3 and switch 4. Interface VLAN 10, IP address DHCP. And then on router 1, if we look at the show IP DHCP bindings, we should see that once those links come up, we should be able to request the addresses. And also, I'm not sure if they have VLAN 10 configured globally. Okay, let's say VTB mode, transparent, VLAN 10. So let's look at the show IP interface brief. We need to make sure that the SVI is in the up and up state, which right now it's up down. So let's say show spanning tree. VLAN 10, we need to make sure we're forwarding first, which this is going to be the reason why. So let's say show run interface. Now show run pipe begin 019. These links should be, that's what the problem is, they're not trunking right now. So let's say interface range fast Ethernet 19 to 24. Switch port trunk encapsulation is .1q. Switch port mode is trunk. Okay, also for simplicity to speed this up, let's say also spanning tree mode is rapid PVST. Okay, so now the VLAN interface is up. If we look at router 1 and now look at the show IP DHCP bindings, we should see that the switches should start to request a lease here, and you may need to flap the links. So let's say show spanning tree VLAN 10. Okay, now we have the assignment. So if we look at router 1, show IP DHCP binding, okay, we have the 3 allocations. So one of these is switch 2, one of them is switch 3, one of them is switch 4. We don't necessarily know which one yet. We could correlate the hardware identifier or the client ID here to the MAC addresses of the ports, and then we would see who has which assignment. But it doesn't really matter who is who, it's just that we do have an assignment from the clients that are requesting the addresses. Okay, so we see without DHCP snooping, the basic allocations are working correctly. Now the next step is to turn the feature on. So we're going to go to switch 1, who's in the middle, and say first IP DHCP snooping. And IP DHCP snooping is going to be on for VLAN 10. Okay, next step on all of the switches, we're going to go to VLAN 10 and shut it down. Then on router 1, we're going to clear out the binding database. So clear IP DHCP bindings. And if we show IP DHCP bindings, okay, we see that we don't have any mappings. Okay, next on router 1, we're going to debug DHCP detail. This is going to show the actual discover messages coming in from the clients, and then ultimately router 1 should reply back with an offer message. So next, let's go back to VLAN 10 and say no shutdown. That's going to be on the other switches. The port should come up and they should start to send their DHCP discovers. Okay, if we look at the switch in the middle, which is switch 1, and look at the show IP DHCP bindings, or no, show IP DHCP snooping, it says that DHCP snooping is enabled for VLAN 10. It's operational for VLAN 10. And if we look at the DHCP snooping, let's see, statistics. Packets forwarded, packets dropped from untrusted ports. We should see on router 1, if we show debug, that's DHCP client. I need to say debug IP DHCP server packets and server events. Okay, on the switches, let's also say the same thing. Debug DHCP detail. This is actually the client request, not the server reply. Then let's say on VLAN 10, we shut it down. Then no shutdown. Okay, it says we're sending a DHCP discover. Notice that it's retrying, though, over and over and over. If we look at router 1 right now is not receiving the packets. The reason why is that we need to make sure to trust the port that's going towards the server. So just enabling DHCP snooping globally is not going to be enough. We need to make sure that either the trunk link that goes to the next hop switch needs to be trusted, or the physical port that goes directly to the server. So in this particular case, when we look at our topology, if this is where the server is located on switch 1, we need to make sure that this is a trusted interface. So by default, all of the links are untrusted in DHCP snooping. So on switch 1, I need to go to that port, fast Ethernet 1, and say IP DHCP snooping trust. Okay, we can see now that we're starting to receive the relay information. Okay, also notice that we're getting an error message basically inside of router 1's output. And let's flap the interfaces again. So we'll shut down the VLAN interfaces and say no shut. Router 1 says the relay information option exists, but the gateway IP address is 0. Inconsistent relay information. Basically what this means is if you don't read the documentation properly, this is kind of an obscure problem, but it exists by default, is that when the switch that's running DHCP snooping, it goes to relay the information to the server, But before it does that, it inserts what we call the DHCP information option. Now, the information option is usually used in large DHCP deployments, let's say like cable modems, for example, that when your end host sends out a request, it says who is the device that forwarded the DHCP discover message towards the DHCP server. So basically, who did the relay? Now, based on who did the relay, the DHCP server should be able to look at its pools and figure out, based on the subnet that the relay is on, I match it up against the pool and then figure out what address do I want to give to the client. But the problem is with the DHCP snooping implementation, the switch inserts the option as empty. And in certain server implementations, like the iOS variation, it means that the DHCP server rejects the packet. Now, there's two different solutions to this. We could either tell the relay not to insert the information option. So on switch 1, we could say no IP DHCP information option, or we could tell the server to trust the 0 field. Now, I'm not 100% sure in the iOS server whether you can actually do that. So the easy way to solve this, though, is to just go to switch 1, and we're going to say no IP DHCP snooping information option. So don't set the gateway IP address. We should now see that when the relay comes in, we should see now the GI address is not going to be 0. So let's flap those interfaces again. Actually, I don't even need to do it. There we have the allocations. Okay, once we're eventually done with this on router 1, if we look at the show IP DHCP bindings, we see the mappings. We now allocated them .5, .6, and .7. Now, when we look at here the client identifier and the IP address mapping, and we look at the switch that's running DHCP snooping, we should have almost an identical copy of this info now installed in the layer 2 switch. If we look at the show IP DHCP snooping bindings, now we have the mapping. So this is one of the main goals of the feature. So beyond stopping the spoofing, the DHCP snooping device is going to keep this binding database, that it now knows what's the mapping between the MAC address of the end host, what's the IP address, and what's the port that they're located on physically. Now, what this is going to allow us to do is to take this feature one step further and to enforce filters in the data plane by using this mapping table. Now, the first of these is called dynamic ARP inspection, or DAI. What DAI does is to prevent an attack on the ARP cache where the attacker sends an unsolicited ARP reply, or what's known as a gratuitous ARP, in order to basically do a man-in-the-middle attack. So for example, if we were to say that the router on the segment, let's say we have router 1 that's connected to the layer 2 switch, so switch 1, and then we have the victim and we have the attacker. Let's assume that router 1's address is .1 and its MAC address is A. The victim's IP address is .2 and the MAC address is B. The attacker's IP address is .3 and the MAC address is C. Now, when the victim learns about the DHCP scope and it says my gateway is .1, what does it need to do in order to actually send traffic to router 1? It needs to ARP. It needs to figure out what's the mapping between your IP address .1 and the MAC address that I'm actually going to use in the Ethernet frame inside of the layer 2 header. So the victim here is going to send out an ARP request. Router 1 is going to reply back with an ARP reply saying that my MAC address is A and my IP address is 1. Now, once this information is installed, though, there's nothing stopping the attacker from sending another ARP reply where the ARP reply says that IP address .1 is actually MAC address C. And the ultimate result of that is that the attacker is redirecting the traffic from the victim to itself as opposed to the router. Because for IP version 4 ARP, there is no security built into it to say that you're not allowed to send a gratuitous ARP reply without someone having sent a request to begin with. Now, as we'll talk about later in IPv6, there are some new advances and fixes for this in IP version 6 that are related to secure neighbor discovery, or SEND, S-E-N-D. But in the case of IP version 4, there's nothing to stop this. So the way to fix this, similar to dhcp snooping, is basically to filter out who is allowed to send an ARP reply, and we're going to base this information on the dhcp snooping binding database. Because if we already heard what are the IP addresses that the dhcp pool allocated and what are the MAC addresses of the client that requested it, if we then enforce in the ARP replies the mapping between these two, then no one should be able to spoof any addresses. So for example, if we were to say on switch 3, when we show run on interface VLAN 100 or VLAN 10, let's say on interface VLAN 10 that our MAC address is MAC, actually we can't change the MAC address, so let me see, can we do it on switch 2? I think these are running different versions. Actually, what I could do is, let's see, let me try this. Let me go to one of the routers and see if, and cap.1q10, IP address, dhcp. Let's see if the switch will hear the, allocation there. I think it won't actually, because it's not in the, no, it's not in the forwarding path for that host. So we can't actually look at it by changing the MAC address, but essentially what we do is to enable ARP inspection for the particular VLAN, and then it's going to enforce the mappings by the dhcp binding database. So for example, and maybe if I change the IP address, we might be able to see it that way. So globally, we're going to say IP ARP inspection, and it's going to be for VLAN 10. And then on the link to the router, we need to say IP ARP inspection trust. Basically, because this is a layer 2 trunk link, there's going to be multiple ARP replies coming in. So normally the link that is your dhcp trusted interface should also be your IP ARP inspection trusted interface. And if we were to then look at the show IP ARP, inspection, says it's enabled and operational for VLAN 10. And let's try this. Let's say that we ping 192.168.10.1. And let's say now on the VLAN interface, I'm not sure whether this is actually going to enforce it or not. But let's say that I manually change the address. And then ping the same destination again. Yes. So basically what happened is that the switch is saying someone with the IP address .44 is claiming that they own this MAC address. But based on the dhcp snooping database, we saw that someone with a different IP address owns it. So essentially what should happen now is that even though we have a valid address on the segment, we shouldn't be able to send traffic to the destination because the ARPs are going to be dropped. So it's essentially preventing spoofing in the data plane because the switch with the dhcp snooping binding database knows what the correct mapping between the two addresses are. Now, even if we weren't doing dynamic ARP inspection, so this is one of the additional features onto it. The other feature that we can also run, which is to enforce this in the data plane on every single packet, is the IP source guard feature. So IP source guard, you could basically think of this like an ACL that is automatically applied based on the dhcp snooping database information. So if I know that IP address .1 belongs to MAC address A and is located on port 1, I'm going to say that every single packet that comes in on port 1 must be coming from IP address .1 and it must be coming from source MAC address A. Now this one we configure it at the interface level where we say IP verify source. This is going to be on the links that are facing downstream towards the access layer. So in our particular design here, we would say that or if we look at it from the logical point of view, we would say that in the case of In the case of the DHCP trust, that would be on this port here, and the ARP trust, so that's on the upstream link facing towards the DHCP server. Then this link and this link here, these are the ones that we configure the IP source guard on. So we would say specifically in this case that on the layer 2 ports, essentially. So if we look at the physical diagram, basically these ports here, we would say interface range fast Ethernet 19 to 24, IP verify source. We can also do this against port security. If we already had port security on to learn the MAC addresses, we could run both of those at the same time. Then that would not necessarily need dhcp snooping. Now we'll see in both cases for ARP inspection and for IP source guard, you don't necessarily need dhcp snooping, but it's going to simplify the deployment a lot because the switch already knows the mappings between the two. It knows the mappings between the MAC addresses and the IP addresses. So now if we were to actually try to send a packet, like on switch 3 here, the one that we spoofed the address, we should see that switch 1 should stop this in the data plane. Okay, so even if we were to turn the ARP inspection off, let's say show run include ARP. So let's get rid of that. Let's say no IP ARP inspection for VLAN 10. And we say show IP verify source. And it says logging is disabled. So how do we enable logging? Let's say IP verify. Let me take a look at the documentation. The features here are under 2 separate documents, but normally you run all 3 of these together. So if you go to the Catalyst configuration guide, this is going to be under DHCP features and IP source guard, and then also dynamic ARP inspection. So let me see under IP source guard, I need to figure out how do we turn the logging on. And then we'll come back to some other details here shortly. So let's search for log. Configuring smart logging. We say logging smart log. I'm not sure if that's going to send that to the console, though. I'm not sure if this is going to work for IP ARP inspection smart log. I'm not sure if this is going to work without an export source. Let's see if I can do that at the link level. Let's say IP or interface range faster than at 19 to 24. IP verify source smart log. No exporter configured. So I think it can't log the packets is what it is unless there's an actual server that I can send these to. But we can see from the switch's point of view, the packets are getting dropped because we should be able to just normally ARP for the destination, and since we're on the same LAN segment, we should have IP connectivity to each other. But if we were now to go back to when we had DHCP configured, so on the LAN segment, if we say instead of manually configuring the address, let's say that the IP address is through DHCP, and show IP interface brief. Okay, we have an address. Now our address is .9. And if we ping 192.168.10.1, now we can reach it. Because now the switch is basically saying that when we show IP dhcp binding, no, dhcp snooping binding, it knows that this address .9 is the one that has this MAC address on that particular port. Now, one of the potential limitations of this is that if you don't have DHCP running, because figure not all hosts in the network are going to get a dynamic allocation, because you might have devices like a printer or an IP phone. Well, IP phone would get it from DHCP, but anything else that would be a static assignment in the network, maybe like a wireless access point, that if you're doing this enforcement of the dynamic ARP inspection and IP source guard, it's not going to have an entry in the binding database in order to validate against. So for any devices that have static addresses, what you need to do is do a manual binding for it that IP ARP inspection or dynamic ARP inspection and IP source guard can then use. Now in the case of ARP inspection, the way you do this is with an ARP ACL. That we would basically say, this is the IP address of the router or the AP or whatever the static address is, and then this is the MAC address that it has. Then we apply the ARP inspection filter to the VLAN for that particular name. Now the same is true for IP source guard, where we would do an IP source binding globally that has the IP address to MAC address mapping. But otherwise, if we use DHCP snooping, it's going to solve this inherently. So in most real deployments, you simply turn all three features on, and as long as all of the downstream links are using DHCP, then everything is going to be fine. But if you have static servers or any other static application, you would need to do both an ARP ACL to do the mappings between the two of them, and the IP source binding to do the mappings between them. Okay, there's a couple questions here. So if the DHCP server were 2 or 3 switches away, we would need to trust all of the trunk links between them. Yes, that's correct. So in a real deployment, normally where you would do this is just on the access layer. So on the access layer, you would trust the upstream facing interfaces, either towards the aggregation layer or the core of the network, and then all of the downstream links would be untrusted from the perspective of DHCP. Then when you do the ARP inspection, likewise, the upstream, the northbound pointing interfaces would be the ones that are ARP trusted, the southbound facing links are untrusted. And then for IP source guard, you would apply the IP source validation or the IP verify source on the southbound facing links towards the end hosts, and the upstream links you wouldn't do that because that's where the routers are located. There's a question, you can tell the router switch to trust the information option in the interface configuration mode. I think that is, let's see, is that a function of DHCP snooping or is that a function of the DHCP server though? The DHCP server we are going to come back to, so I'm not going to get too in depth with it, what are the other features, but let me check this real quick. This would be under IP addressing configuration, DHCP configuration, then let's try the DHCP server and let's look for the DHCP server can allocate dynamic addresses based on the relay option, which is option 82. This we're going to come back to because this actually gets really complicated how you need to do the mappings between them. The easy way to do it is like I did on the switch, which is just to tell it to stop inserting the information option. Because otherwise on the router we have to do basically a mapping to it, and there's a couple other steps that we would have to go through. So if we look at here on switch 1, the final config, if we show run pipe include DHCP or ARP or verify, we would say, and also I had IP ARP inspection. I turned it off before. Let me turn that back on. This. So these first 3, actually the first 4, these are global. These two are on the northbound links. Okay, basically to the DHCP server. These ones here are southbound to the access layer. So you can see the configuration is not that complicated. There's only a couple commands that are needed for it. And if you don't configure this on the access layer, it is very, very easy to implement the attack. There's a lot of tools that you can download, and basically you just plug a single link into the network, and then you could redirect all traffic from the devices on the LAN locally, sniff that, rewrite it, and forward it onto the router. And the thing that's very dangerous about this attack is that when you look at the latency of redirecting a packet from the victim on the LAN and then out to the WAN, since the LAN is so much faster than the WAN anyways, that if this is gig E on the LAN, the end client is not going to notice a difference if I have an extra 5 milliseconds of delay when the packet is going out and then coming back in. Because we may say that the WAN speed is, whatever, 10 megabits per second, and if your LAN is gig E, it's going to take such little time for it to rewrite the frame and go out that the application wouldn't even notice the difference. Because you still are able to get to the legitimate applications, it's just that on the first hop LAN segment, it's redirected to somebody else in the middle to begin with. And the only way that you would detect this from your application, from the victim's point of view, would be to look at the ARP cache and then correlate that to what is the actual MAC address of the router. And it's something very obscure that you wouldn't normally look at, because if everything is working to begin with, the victim is not even going to know. Now again, we'll also see this a little bit later in IPv6 with the IPv6 first hop security protocols, but it's basically the exact same problem that we're trying to prevent. That when we do the neighbor solicitations and the neighbor advertisements, the router solicitation and the router advertisement, we want to make sure that there's not an additional attacker on the LAN segment that's able to spoof the router by sending unsolicited ICMP NDRAs, the router advertisements, which is going to have the same effect as the ARP spoofing attack like here in IPv4.